Welcome back, calculus fans. Today we're going to be looking at the graph of f and how we can deduce it from learning about the first derivative and the second derivative. So we'll get into several big ideas relating the derivatives of f. Some of the things we have noted is that f has a max when f prime goes from positive to negative, and f has a min when f prime changes from negative to positive. Now, what happens in here? Remember, that's where we would have a critical point, and that's where the derivative would either be 0 or undefined. This is known as the first derivative test to see if there's a max or a min. We've also noticed the following, and this is really important too. If f is an increasing function, that happens exactly when the derivative is greater than 0, and if f is decreasing, that happens exactly when the derivative is negative. So those go back and forth. They're if and only if statements. So here's an example that'll help us get some idea of what we're talking about. What we want to do is find the extrema, the relative max and mins, or maybe absolute max and mins, and sketch the graph of the function x squared minus 3 times e to the x. So we begin by taking the derivative, and the derivative we need the product rule, and so it's going to be the first times the derivative of the second plus the derivative of the first times the second. So there's the derivative, there's f prime, and what we can do is manipulate this a little bit algebraically by factoring out e to the x, and we get x squared plus 2x minus 3, which we can write as e to the x times x plus 3, x minus 1. There we go. So what does that tell us about the derivative? Well, it's pretty easy to see that this is always positive, so it really doesn't contribute anything to the sign, S-I-G-N, of the derivative. But we see that the derivative is going to be 0 when x is negative 3, and 0 when x is 1. And in fact, this is simply a quadratic opening up, so it's pretty easy to analyze it. And what we'll introduce here is the concept of a sign chart. Very helpful to help organize information. And it works like this. I'm going to make a chart, and here's x, and the key points here are minus 3 and 1. And I'll analyze the derivative. And as we just said, the derivative is going to be 0 here and here. To the right of 1, the derivative will be positive. Between these two roots, negative. And to the left of minus 3, positive. So what does that tell us about f? Well, remember what we know. If the derivative is positive, my function is increasing, decreasing, increasing. So right here we have a max, and here we have a min. And that is a very simple way, this sign chart, of displaying the information and helping us see exactly what's going on between the first derivative and the function itself. So what we'll do now on the next page is make a sketch of this graph, remembering that we have the behavior increasing, max, decreasing, min, increasing. Okay, so let's sketch this graph, knowing what we know. And remember, we know that we have a max at -3, so at -3 it's going to look something like this. And we have a min at 1, it's going to look something like that. And for right now, that's about all we know. And so the graph is going to behave like this. And over here, it's going to behave like that, with an asymptote. And that's because everywhere to the left of -3, my function is going to be positive, but e to the x will dominate it, and we'll see why in a few weeks. And as x approaches -infinity, e to the x approaches 0. And the fact that e to the x approaches 0 dominates the fact that x squared minus 3 is getting large. So now let's talk about the idea of concavity, where the first derivative tells us about the direction, increasing or decreasing. We'll see that the second derivative tells us about concavity, which basically describes the shape. So here's what you need to look at. This graph right here, as we move along it, think about what's happening with the derivative. The derivative is very, very negative, becoming less negative, but still negative, becoming less negative. Right here, the derivative is 0. Now the derivative is just a little positive number, and as we move along, the derivative is getting greater and greater and greater. So what we notice here is that the first derivative is increasing. Similarly, if we look over here, right over here, the first derivative is very, very positive. And as we move along, the derivative is still positive, but becoming less positive. Here the derivative is 0. Here it's negative. And as we move along, the derivative is becoming more and more negative. So on this graph, we see that the first derivative is decreasing. We call a graph on the left, we say that this graph is concave up, and we call this graph concave down. Now let's take a second here and remember what we learned previously. If a function is increasing, then its derivative is positive. Well, here we have this function increasing, so its derivative must be positive. And the derivative of the first derivative is the second derivative. Similarly here, our conclusion is that the second derivative must be negative. So what we learn from this is that a graph will be concave up exactly when the second derivative is positive, and a graph will be concave down exactly when the second derivative is negative. So just to summarize these two ideas, the first derivative tells us about the direction, whether a graph is increasing or decreasing. The second derivative tells us about shape, whether a graph is concave up or concave down. So let's consider the following definition of point of inflection. And what we're going to talk about here is what it means to have a point of inflection. And that's simply a point on the graph at x equals c where the concavity changes. Now, the concavity changes. Here we're concave up, here we're concave up, and now we're concave down, now we're concave down. So what this is showing you is that right about here we have a point of inflection where the concavity changes, where it goes from either being concave up to concave down or vice versa. You might think that if the second derivative is 0 that we get a point of inflection. That's not necessarily true. Just like if the first derivative is 0, we don't necessarily have a max or a min. And the best example to think about here is y is equal to x to the fourth. If we take the second derivative, we see we're going to get 12x squared. And the second derivative is 0 when x is 0, but the graph of y equals x to the fourth has no inflection point. And that's because when we look at the second derivative, except at 0, it's always positive. So that means my graph is always concave up. So let's summarize on this new idea, and this is called the second derivative test for extrema. And it simply says this, that if the first derivative at a point C is equal to 0, and if the second derivative is negative, now remember that means that we're concave down, then we have a max at x equals c. Similarly, if the first derivative is 0, and if the second derivative is greater than 0, that means we have a min at x equals c. And that's a way to tell, using the second derivative, whether we have a max or a min. So let's just look at this. In the first case, I'll call that 1 and we'll call this 2. In the first case, we have a function which is at a point C. The derivative is 0, so it's flat, and the second derivative is negative, so it's concave down. And that's what we get, and that gives us the max. And with the second one, here's our point C. The derivative is 0 here, and we are concave up, so we get a min. And that's the way that looks. So let's conclude this study of the function and its derivatives with this problem. Now what we're given here is the first derivative. The first derivative is equal to 4x cubed minus 12x squared. And what I can do is factor out 4x squared and write this as x minus 3. So if I employ a sign chart here, as we did before, it's a very important point here, and that has to do with the fact that that's a squared, which means that although the derivative is 0 at x equals 0, the derivative doesn't change sign. That's a huge idea. So for our sign chart, we're interested in 0, and we're interested in 3. And let's look at what the first derivative tells us. First derivative is 0 here, and it's 0 here. To the right of 3, the first derivative will be positive. Between 0 and 3, the first derivative will be negative, and on the other side of 0, the first derivative is negative again. The first derivative doesn't change sign when x is equal to 0. So here's what it tells us about f. F is decreasing there, flat here, decreasing still, increasing here, and so what we have is a min at x equals 0. Now, how about the second derivative? Well, the second derivative is equal to 12x squared minus 24x. So the second derivative can be written as 12x times x minus 2. And if we do a sign chart for the second derivative, our points of interest are 0 and 2. And the second derivative is 0 here and here. It's positive here. The second derivative is negative in between those two roots. And it's positive here. So what does that tell us about f? If The second derivative is positive. The function is concave up, concave down, concave up. And so right here, let's see if I can do it, we have inflection. And right here, we have inflection. And so those are all the key ideas that'll help us graph the function f. We know its shape. We know its direction. We know an extreme value. And we know its shape. And we also know where the inflection points occur. So it's too bad I can't fit it on this window. You may need to go back and forth. But let's go ahead and advance this and now sketch the graph. Okay, so let's see how good we can do with this. Remember the derivative was 4x cubed minus 12x squared. So that means the function itself is going to be x to the fourth minus 4x cubed plus a constant. Note that when we take the derivative of this, we get 4x cubed minus 12x squared. Now what else did we know? We know that there is a minimum value when x is 3. So here we are when x is 3, and I'll just show that there's a minimum there. And that's the only extreme value that we found. We also found that at 2, we had a point of inflection. So we're concave up to 2. We also had a point of inflection at 0. So here we are at 0, and there's a point of inflection there. And so here we go. We're concave up, now we're concave down, and then we are instantaneously flat at 0, and then we're concave up. And that's the way we graph f, given that the derivative was 4x cubed minus 12x squared. And just in passing, note that that we have this plus c, so we could take this whole graph of f and shift it up or shift it down, and the graph is correct. So we don't know exactly where these points happen, but the shape and the direction is very clear, and that is something that does not change. So there we go. See you next time.